Welcome back to the deep dive. Today, we're jumping straight into, well, maybe one of the biggest challenges for large language models right now. The fact that they're basically static.
Yeah, it's a strange thing, isn't it? They know so much. I mean, they ingest this incredible amount of world knowledge, but only up to a point. The moment the training run finishes,
Yeah.
that's it. They're frozen.
So they can't easily adapt to new information or learn new skills once they're deployed?
Not easily, no.
Yeah.
Especially if you don't have tons of really specific, high-quality data for that new task. They sort of lack that mechanism for self-improvement.
And that inability to keep learning, that feels like a major bottleneck. So the sources we're looking at today propose a framework to tackle this. It's called self-adapting LLMs, or SEAL. Okay, let's unpack this. The core idea, the big question is, can a language model actually figure out how to teach itself new things? Maybe even better than we can directly teach it.
That's pretty much the mission, yeah. SEAL basically flips the script. Instead of us feeding it data, the model takes charge. It generates or transforms its own training material. It could even set up its own learning parameters.
That sounds pretty radical. The research uses an analogy to human learning to explain it, right?
It does, and it's quite helpful.
Yeah.
Think about preparing for a really tough exam. You wouldn't just reread the textbook cover to cover, would you?
No, definitely not. I'd be making notes, summaries, maybe drawing diagrams.
Exactly. You assimilate it. You actively transform the raw information into something, or like something that clicks better for you. You rewrite it, restructure it, and that active part is key for real understanding and memory.
Right. Passive reading only gets you so far.
And that active assimilation, that's what's missing when we just fine-tune LLMs the standard way. We just throw raw text at them.
So SEAL introduces this concept, the self-edit, or SE.
That's the core mechanism. The self-edit, or SE, is basically the model generating its own instructions in natural language. These instructions specify, first, what synthetic data it should use to update its own weights.
Okay.
And second, potentially, it can even specify the optimization details. Things like the learning rate it thinks is best, or how many training steps.
Wow. So it's like the model is writing its own study guide and deciding how best to study it.
You got it. Its own personalized learning plan.
But hang on. If the model is generating the data and the plan, how do you stop it from just making up nonsense? Or maybe optimizing itself into some weird, useless corner? Isn't there a big risk the self-edit is actually harmful?
That's a really critical point. And the answer is in the architecture. It's a meta-learning system, essentially, with two nested loops designed very carefully to make sure the self-edits are actually, well, good.
Okay, 2 loops. Let's break that down. The first one, the quick part.
Right, that's the inner loop. This is where the model acts on its self-edit. It generates the SE, that synthetic data or instruction set, and then it immediately uses that to update its own parameters, usually with standard supervised fine-tuning, SFT.
So that's the actual learning step. The weight update happens there, like
Yep.
the student writing the first draft of notes.
Precisely. It's a temporary trial update based on the self-edit.
And the outer loop is then the quality control, checking if those notes were any good.
Exactly. The outer loop uses reinforcement learning, RL. Its whole job is to optimize the policy that generates the self-edits in the first place.
Ah, okay. So generating the SE is the action in RL terms.
Yes. And the reward. This is the crucial bit. The reward is the downstream performance of the updated model, the one that just got fine-tuned in the inner loop.
I see. So the model tries an edit, updates itself, gets tested on the task, and if its score goes up, the RL loop says, okay, that was a good way to generate an edit. Let's do more like that.
That's the essence of it. It's learning how to generate edits that demonstrably improve its own performance. It's learning to be a better learner.
Okay, that makes sense. But what about the instability, the risk of it learning to generate garbage?
Good question. They use a specific technique here called RESTEM. Think of it as filtered behavior cloning. It's important because you only want to reinforce the edits that led to a positive reward, a real improvement.
Right, you don't want it reinforcing edits that made things worse or did nothing.
Exactly. RESTEM helps filter out the noise and prevents the model from learning bad habits, basically. It stabilizes the whole meta-learning process, making sure it converges towards genuinely useful self-editing strategies.
Okay, that does sound safer, knowing there's that validation step. All right, this is where it gets really interesting. Let's look at the results. How well does this actually work? Starting with integrating new facts, right?
Yeah, this first test is tough. The goal isn't just like retrieval augmented generation where the model looks up a document. It's about truly absorbing information from a passage, say a squad document, into its weights.
So it can answer questions about it later without seeing the passage again?
Exactly, burning it into memory, so to speak.
Hmm.
And for this task, the self-edit the model generated took the form of implications.
Implications, meaning,
Instead of just feeding the raw, often long and messy passage back into itself for fine-tuning, the model first processes it. It generates a distilled list of logical consequences, maybe key facts restated simply, kind of like atomic pieces of information derived from the passage.
like breaking it down into easy to digest chunks.
Precisely. And that distilled list becomes the synthetic training data for the update, which they did using lightweight LoRa tuning in this case.
Okay, so how did it compare? Let's see the numbers. They used Quen 2.57b.
They did. So the base model, with no adaptation at all, got about 32.7% accuracy on answering questions about passages it hadn't seen in context.
Okay, baseline. And fine-tuning directly on the raw passage text.
Almost no difference. Maybe the text was too complex or noisy. It only nudged up to 33.5%. Basically negligible gain.
Right. Now, what about synthetic data? If the base model itself tried to generate training data without the RL optimization.
Better. Using synthetic data generated by the base Quinn model itself pushed accuracy up to 39.7%. So generating some kind of structured data is clearly better than the raw text.
Okay, getting warmer. But the real test is against, say, data generated by a much bigger, more powerful model, right? Like GPT 4.1.
Exactly. They had GPT 4.1 generate synthetic training data from the passages too. And that achieved 46.3% accuracy, a big jump.
Makes sense. Bigger model, likely better synthetic data. But where did Seal land?
And this is the really striking part. Seal, after the RL outer loop had trained the Quinn model to optimize its own self-edit generation, Seal achieved 47.0% accuracy.
Hold on. It beat the synthetic data generated by GPT 4.1.
By a small margin, yes, but consistently. The 7B parameter Quinn model, trained how to generate the best possible study note for itself, managed to create more effective training data than the much larger GPT 4.1 could generate for it.
That feels significant. It's not just about having the biggest model make the data. It's about the model understanding its own learning process.
I think that's exactly the implication. The RL training didn't just teach it to generate any synthetic data. It taught it how to restructure the information in a way that was maximally effective for its specific architecture to learn from. It distilled the passages into what the paper calls easily learnable atomic facts.
So it found the optimal learning format for itself.
That's profound. It shifts focus from just raw model scale for data generation to intelligent self-configuration.
Precisely.
Okay, let's pivot to the second big application area, few-shot learning. Generalizing from just a handful of examples, they use the ARC benchmark, right?
Yeah.
Abstraction and reasoning corpus. Yes, ARC is notoriously difficult, focused on abstract visual reasoning from very few examples. And here, SEAL demonstrated something different. They call it autonomous configuration.
Autonomous configuration. So the self-edit wasn't data this time.
No. In this case, the self-edit generated by the model was actually a specification, a set of instructions for how to set up its entire adaptation pipeline for the ARC task.
So it wasn't just choosing the data, it was choosing the learning strategy itself. What kind of things was it choosing?
It was meta-learning on steroids almost. The model's generated SE would specify things like which data augmentation techniques to use should it rotate the input examples, flip them, resize them.
Wow.
And it also specified the optimization parameters, like the exact learning rate to use, the number of training epochs, even the specific type of loss function calculation that would work best for this particular ARC problem. It was designing its own test time training setup.
That really is learning to learn. Okay, so how did that perform? They used Llama 3.21b instruct for this.
That's right, a smaller model. And the baseline, standard in-context learning, just showing the examples on the prompt, 0% success rate on the ARC subset they used.
0? Ouch. Okay, what about just applying test time training, TTT, but without SEAL optimizing the configuration for?
Better than 0, but still not great. They got a 20% success rate. So some adaptation helps, but a naive setup isn't enough.
And SEAL, the model that shows its own augmentations and learning rate.
A massive jump. The SEAL-configured approach achieved a 72.5% adaptation success rate.
From 20% to over 72%. That's huge.
It really is, and it shows the versatility, doesn't it? SEAL isn't just about generating factual data. It can learn the process of learning, too. It figured out the optimal configuration, the right tools, the right settings for this specific, challenging reasoning task.
These results definitely paint a picture of more dynamic, adaptable LLMs. But it can't be all smooth sailing. The sources mentioned limitations, costs. What are the catches?
Well, the age-old problem in continual learning hasn't magically disappeared. Catastrophic for
Ugh, CF. Learning new things makes it forget old things.
Basically, yes.
Hmm.
While SEAL works well for adapting to a single new piece of information or task, the research showed that if you update the model sequentially learn passage A, then passage B, then passage C, the performance on passage A does start to degrade over time.
So it's still susceptible.
It is. The current SEAL framework doesn't have explicit mechanisms built in to prevent forgetting. It establishes a baseline for adaptation, but future work would need to layer in techniques specifically for knowledge retention alongside SEAL.
Okay, that's one limitation. And the other big one was cost, computational overhead.
Oh yeah, this is probably the main bottleneck right now, that RL outer loop, the part that optimizes the self-edit generation. It's expensive.
More expensive than typical RL for LLMs.
Significantly more, because of how the reward is calculated. Remember, the reward is the performance of the updated model, which means for every single candidate self-edit the RL algorithm wants to try, you have to actually perform the inner loop. Take the base model, apply the fine-tuning using the candidate SE, and then run an evaluation on the fine-tuned model to see how well it did.
So you're essentially fine-tuning and evaluating a whole LLM just to get one reward signal.
Exactly. And each one of those evaluation cycles, according to the paper, took about 30 to 45 seconds on their hardware.
30 to 45 seconds per potential edit. And RL needs to explore thousands, maybe millions of possibilities.
Wow, that sounds incredibly computationally intensive. Less like a deep dive, more like deep pockets needed.
It really is a substantial cost. There's no getting around that currently.
But despite that cost, you're saying frameworks like SEAL are becoming kind of essential. Why?
Because of something looming on the horizon. The data wall.
Right, the point where we basically run out of new human-generated text on the internet to train these models on. Exactly. Projections vary a bit. But the consensus is that frontier models are on track to exhaust most high-quality, publicly available text data, maybe as soon as 2028, maybe a little later.
So we can't just keep scaling by throwing more human data at them indefinitely.
Correct. Future progress, especially for improving things like complex reasoning or reliable instruction following, likely won't come from just finding more websites to scrape. It has to come from the models getting better at generating their own useful training signals.
So synthetic data generation goes from being a nice-to-have to a fundamental necessity.
Pretty much. And SEAL is a really interesting step in that direction, not just generating data, but learning how to generate the most effective data for self-improvement. It's a pathway towards generating maybe even novel pre-training corpora, or enabling genuine self-learning cycles in a data-constrained world.
You can imagine this fitting into agentic systems too, right? Models interacting with the world.
Absolutely. That's the long-term vision, I think. Imagine an AI agent interacting with an environment. It tries something, maybe it fails. It could then synthesize a self-edit based on that interaction. Okay, next time I encounter situation X, the key implication is Y, and I should update my policy with Z parameters.
Triggering a weight update right there.
Exactly. Allowing the agent to continuously develop, adapt, and refine its knowledge and behaviors over its lifetime based on its own experiences.
Okay, so let's try to wrap this up. Our deep dive into self-adapting LLMs, SEAL. It's a meta-learning framework that lets these typically static models take control of their own adaptation. They generate their own optimized training data, their own fine-tuning instructions,
They self-ed.
which leads to some pretty significant performance boosts. We saw it in knowledge incorporation, where it actually outperformed synthetic data from GPT 4.1.
Which is quite something.
And also in Q-shot reasoning on ARC, where it learned to configure its own learning strategy, leading to a massive jump in success rate.
This raises an important question.
Always does.
Given that huge computational cost, we talked about fine-tuning a model, just to get a single reward signal, how will future systems balance that? How do you weigh the immediate benefit of making a specific self-edit against the sheer cost of updating the model's entire knowledge structure? Especially as we move towards models that are supposed to learn continuously over long periods, maybe inside complex agents. Where's that trade-off going to land? Something for you to mull or explore on your own.
A critical question indeed. How much self-improvement is worth the price? So, what does this all mean? Stay curious, and we'll see you for the next deep dive.